Hello everyone. So let's start discussing LU decomposition today. So our topic is LU decomposition. So uh, uh, we have already discussed Gaussian elimination process uh, where we have manipulated a matrix uh, to get a upper triangular matrix using row elementary operations, which helped us to solve a system of linear equations. So, so the thing is, why do you want to decompose? Why would you want such a decomposition like a decomposition? So basically, this thing is important uh, for the for storing data. Uh, so that's why usually engineering students like to use LU decomposition. So let's not go there. That is not our headache. So let's see what is LU decomposition. So basically, here we start. Let's start with the uh, square matrix. Let's say n cross n square matrix. And what is LU decomposition? Basically, we want to decompose this matrix as multiplication of two matrices L and U, where L is lower triangular matrix and U is upper triangular matrix. Okay. So usually the obvious question will appear in your mind is when we can decompose a matrix, or can we decompose every matrix, every square matrix? Obviously we are talking about square matrices. So the way I will say, so let's start with an example. So you can see that uh, let's take this matrix. So the question is, can we decompose this matrix in LU form? So for now, for timing, let us assume that we can decompose. Okay. Assume A equal to LU. Let's write it this in proper way. L11. So it is a lower triangular matrix. So these two elements will be 0, right? Right. And here it comes the upper triangular matrix. How will it look like? So upper triangular, that means this element will be 0, right? So this is the way we shall write. So and the left hand side is 0 1 0 1 0 0 0 0 1, right? So just multiply these two matrices. So you can see that by multiplying these two matrices, the first element will be L11 U11, which will be equal to the left hand side matrix. So this will get equal to 0. So that will imply that either L11 equal to 0 or U11 equal to 0, right? So see that if any of them equal to 0, let's say without loss of generality, let's take this one L11 equal to 0. See that if L11 equal to 0, then this matrix, this lower triangular matrix, has determinant 0. So determinant of L equal to 0. And we know that determinant of L U equal to det L equal to into det determinant to U. it get multiplied, right? So that will enter that this matrix, this for the multiplied matrix has determinant 0. And what, so the right hand side matrix has determinant 0. Now let's look at the left hand side matrix. uh, what is the determinant of the left hand side matrix? You can see that this determinant, this matrix has determined either 1 or minus 1 equal to, it basically not equal to 0. So that's the contradiction. Basically the uh, this example says that we cannot decompose this matrix A in LU form. So we got our first answer, that we cannot decompose all matrices in LU form. Now let's check. You guys already, do you guys know about permutation matrix? So what is permutation matrix? We, we say matrix P permutation matrix. Let's write it proper way. Permutation matrix. If basically whenever you if 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 we get it by interchanging rows of आइडेंटिटी मैट्रिक्स, बेसिकली तुम अगर आइडेंटिटी मैट्रिक्स जो भी होंगे उनका अगर रोज भी इंटरचेंज करोगे, जो मैट्रिक्स मिलेगा वो परमुटेशन मैट्रिक्स है। तो अगर परमुटेशन मैट्रिक्स से तुम कुछ मैट्रिक्स को मल्टीप्लाई करोगे तो वो जो ऑपरेशन तुम परमुटेशन मैट्रिक्स पे कर रहे थे ना, आइडेंटिटी मैट्रिक्स पे, those operations will be applied on the matrix on which you have multiplied, right? So let's take the permutation matrix 0 1 0 1 0 0 0 0 1. Basically we have interchanged the second row and the first row. So if we multiply P with this matrix A, so that will be, you shall get the identity matrix back, right? So now see that this is already in LU form, because you can write this I cross I, right? So identity basically diagonal matrix, तो diagonal matrix को तुम दोनों फॉर्म में देख सकते हो, लोअर ट्रायंगुलर अपर ट्रायंगुलर, दो बात हो गया खत्म। सो तुमने देखा कि एक बार तुम इसको नहीं कर पा रहे थे डिकम्पोज, तो उसके बाद परमुटेशन मैट्रिक्स मल्टीप्लाई करके तुम उसको डिकम्पोज कर पा रहे हो। सो द थिंग आई वांट टू से इज any matrix, if you take any square matrix, if either it is decomposable or after multiplying with permutation matrix is decomposable for some permutation matrix P, right? So that's the thing. Now the question appears that you want to say that when does the how do we know that it is decomposable or not? So there is a uh, particular document in, you can find in Wikipedia. Let me open it for you. So I will also attach this link in the description of the video. Right, so decomposition. Oh, here it is. So what it says there. So let's see this first one. It says that if A is invertible, it's saying that if A is invertible, अगर तुम्हारे पास जो मैट्रिक्स है अगर इन्वर्टिबल होगा, then it admits an LU decomposition if and only the leading principal minors are non-zero. तो क्या बोल रही है? So ये जो प्रॉपर्टी है ये उन्हीं मैट्रिक्स पे वैलिड होता है जो इन्वर्टिबल है. So let's take A invertible matrix, right? So we have started with an invertible matrix, and now we want, so we say that A is decomposable if and only if all the leading principal minors are non-zero. What does this mean? So if you start with this matrix, let's say 1 A1 2 A1 3 A2 1 A2 2 A2 3 A3 1 A3 2 A3 3. So you have started with this matrix. Let's assume A is invertible, basically determinant of which doesn't equal 0. And what is the saying? They are saying that we shall say that this matrix is value decomposable if the all leading principal minors. What are those leading principal minors? So leading principal minors, from the definition you can see that the definition of leading principal says that this is a leading principal minor. If you take determinant of this matrix, this is a leading principal minor, and determinant of the whole matrix, this is a leading principal minor. So basically they are saying that in addition with this one, A11 doesn't equal 0, date of A11, A12, A21, 22 doesn't equal 0, and another leading principal minor, the whole matrix, basically date of A does not 0. If all those three are true, then we can say that A is highly decomposable. So this is an necessary sufficient condition to predict if an invertible matrix is highly decomposable or not. So after that, so let's go back to that page. So let's focus here. There is another, in general, characterization kind of thing. So they are saying that in general, any square matrix, they are taking any square matrix, could have one of the following. बोल रहे कोई भी स्क्वायर मैट्रिक्स तुम उठाओगे, वन ये तीनों में से कोई एक होगा ही. आइदर इट हैज यूनिक एडिव फैक्टराइजेशन, बोल रहे हैं जो तुम ले रहे हो उसका यूनिक फैक्टराइजेशन होगा. ठीक है, मतलब तुम अगर उसको एक अगर एल यू और एल वन यू वन फॉर्म में लिखोगे तो ये एल वन एल दोनों सेम होगा, यू वन और यू दोनों सेम होगा. ठीक है, उसके बाद बोल रहे हैं इन्फाइनली मैनी वैल्यू फैक्टराइजेशन, बोल रहे हैं ऐसे हजारों ऐसे तो काउंट मोर देन फाइनाइट इनफाइनाइट ऐसे वैल्यू फैक्टराइजेशन मिलेगा इफ टू और मोर ऑफ द फर्स्ट एन माइनस वन कॉलम्स आर लीनियरली डिपेंडेंट. बोल रहा है टू और मोर, या तो दो या दो से ज़्यादा ऐसे कॉलम्स लीनियरली डिपेंडेंट होंगे. यू गाइस ऑलरेडी नो द डेफिनेशन ऑफ लीनियरली डिपेंडेंट. लेट मी राइट इट once again if you do not recall. So two vectors, let's say you have these vectors, these two vectors. You will say these two are linearly dependent if there exist non-zero real number x and y such that this equation holds. So then we say linearly dependent. Then we say these two vectors are linearly dependent. So this you can continue in general, like more than two vectors you can also consider, and infinite number of vectors you can also consider.